Good morning, everyone. It's my great pleasure to chair this session on the Rietz Lecture to be given by Hans-Georg Müller, who is a distinguished professor at the Department of Statistics at UC Davis. Professor Müller has made some deep and broad contributions to statistics, ranging from fundamental advances in functional data analysis and the statistics of stochastic processes, all the way to applications in brain imaging and plant genetics. The Rietz Lecture is named after the first president of the IMS, Henry Rietz, and it's awarded only every 3 years. So it's one of the highest honors awarded by the IMS. So please join me in congratulating him on receiving this award. Okay, great. So we're very much looking forward to it. Thank you very much.
Thank you, Rajan, for your kind introduction. It is a great honor for me to give the Rietz Lecture 2022. And I wish to acknowledge 5 collaborators who have contributed greatly to the work I'm going to present. Indeed, they did most of the heavy lifting. So the first one is Alex Pedersen, who is in transition from UCSB to BYU. Then Ya-Ching Chen, she's currently still at Davis, but in transition to Rutgers. Senwa Lin, who is for a couple of years at National University of Singapore. And then Paramita Dubey, who is currently at USC. And Zhang Bo, well, his face is obscured here, I'm not sure if I can get this off. Zhang Bo Su, who is in transition to Notre Dame. So these brilliant young statisticians have greatly contributed to my presentation, to the work I'm going to present. So I'm going to talk about random objects, by which I mean complex data that take values in a metric space, which I call omega d. There is some sort of underlying probability measure. Such data are quite common, but have been underappreciated in current statistical methodology and theory. So there's a lot of open problems which could make this an interesting area for future research. So the idea is that there is no area yet which could be called metric statistics, where we are looking at data in metric spaces. And so I'm going to focus on some tools to explore such data that live in metric spaces. I will focus only on 2 main things. One is depth and related notion of quantiles, and the second is regression. So these are the topical points. There are a lot of more, of course, features and problems that arise in this area. So there are some basic assumptions. I will not do this very mathematically, which means that I just list the assumptions once and for all. The space has to be separable, totally bounded, and satisfy some entropy conditions. Now, those kind of conditions you have to verify on a case-by-case basis for each metric space separately. So a key toolbox is the connection to empirical processes for the whole thing. So all the results use empirical process theory one way or other. Okay, so what are random objects? Well, there is the classical case of random functions, which are usually considered infinite dimensional data in Hilbert space. And that constitutes a field of functional data analysis, which has been very well developed and is facilitated by the fact that we have a vector space structure and we even have an inner product, so we can define projections, which is not the case, of course, in geometric spaces. Singh and Eubank have a very good summary of the analysis and linear operator tools that you can apply for the case of functional data. A second big area or situation which has been considered for a long time are finite dimensional Riemannian manifolds, for example, spheres SP embedded in RP+1. That has constituted a field of geometric statistics that's very well established. But still there are surprising results, for example, regarding certain distributions on spheres and central limit theorems with non-traditional rates. Now, a third class of random objects are random distributions. This is an area that has been coming up in the last 5 years, I would say, only from a statistical perspective. That is, which means you have a sample of such random distributions. And there's the emerging field of distributional data analysis. Peterson, one of my collaborators featured in the beginning, has a review paper in 22, which details some features of that. This is particularly of interest for one-dimensional distributions, not so much for multivariate distributions. Then we have symmetric positive definite matrices and also surfaces. Symmetric positive surfaces arise if you have samples of stochastic processes where the covariant structure is a SPD surface. And interestingly, there are every couple of years there's a new interesting metric. Jung has one 2015, very interesting from statistical perspective. And then Lin, one of also the collaborators, has one more recently. Another class of objects are networks that can be represented as graph Laplacians, for example, if they have the same number of nodes. And there are recent works on regression models using such graph Laplacian representations of networks. The last class I want to mention are trees. Phylogenetic trees, of course, are important in biology. And there is the, for example, one of the common metrics on the tree space is the BHV metric, which has been known for a long time to generate a Hadamard space. That means it's a non-positively curved and complete space. And we were recently able to show that it also satisfies the requisite entropy conditions that we want for such spaces. Okay, so what's the general framework and perspective? The idea is to develop a general methodology. For example, quantiles tests, two-sample tests, regression, whatever you have as a statistical toolkit for such random objects. That means sort of create a field of metric statistics. Many aspects, as I mentioned, remain unexplored currently. An early push was a 2010-11 NSF program here at SAMC. So the starting point of this and what constitutes statistical analysis is a sample of random objects. So you have IID sample, and that's our starting point. And then you can discuss particular settings. For example, you can discuss complex settings where you have a omega valued stochastic process observed repeatedly. So this is like functional data, but the observations are in metric space rather than scalars or vectors, as is the common functional data analysis. And so if you have such omega valued processes, you want to do statistics with them, it's highly non-trivial and you have to think about what tools to develop. So when we have a sample of random objects, let's say distributions, you need first to decide on a metric because the metric space is not naturally given in statistics, right? What we have are those objects distributions. We need to think about which metric is the right one to choose. This is a difficult problem that has not been really addressed or resolved in much way. So if you have distributional data, for example, you could use the Fisher-Rao metric, which has some advantages. And what that means is you take, you assume these are nice distributions, have densities, you take the square root of the densities, the integral of the square root of the density is 1, so you are on a Hilbert sphere, right? And then you can define the distance, the Fréchet metric, as the geodesic on the Hilbert sphere, where the formula is this one here. So that's one way, which has the advantage that it works in any dimension. So we are not limited to one-dimensional distributions in any way. Computationally, also very simple. Second, more popular metric is the Wasserstein space with the Wasserstein-Kantorowicz metric, which is very handy for one-dimensional distributions because it's just the L2 metric of the quantile functions. So easy to work with in one dimension. And is connected to optimal transport, which is nice for statisticians, nice, but not necessarily very convincing. What's more important is that this Wasserstein space in one dimension has super nice statistical properties and works very well in data analysis. For the higher dimensional case, it's problematic for many reasons, and the case for statistics has maybe not been made completely if you have samples of such objects, because other metrics are much easier to work with in this case. Okay, so the idea is if we explore a sample. So I'm starting with a case that you have just one sample. And later I will go to the case where we have more than one. If you have just one sample in statistics, you want two things. You want to measure the location and you want to measure the variation of the data. These are the elementary things you want as a statistician. And so, of course, we cannot take an average X bar because we do not have linear operations. But Fréchet in 1948 recognized that X bar, the regular mean, can be expressed equally as the object in a metric space that minimizes the square distances on average. So this here is a Fréchet mean. And there is one thing to say that is not necessarily unique. We don't know what this, how big or small it is a set, right? So you have just to minimize the set of the arguments. If you are lucky, it's just one element, but it can be many. It depends on many features. It depends on the space and on the distribution on the space of your X, the sample data. The empirical version is here. And one thing we know is that if the space is a Hadamard space, that means non-positively curved, then we can have a unique minimizer. Otherwise, it depends. You have to establish case by case. And this is also a very active area, namely to study the convergence of certain estimates of the Fréchet mean to the target. We found particularly one extension of interest in our work, which is the Fréchet integral. We call that Fréchet integral. There's an old notion of Fréchet integral, but it's not really much used, which means that you want to also define the integral of a process x of t that is taking values in omega. So the solution for this, if you want that, very useful for many applications, is that you just take the minimizing element in your space that minimizes the squared distance to the x of t's, and you integrate this over t, and then you take the minimum of this. So you can very easily show that if you have a real valued x of t function, this is the same as the Riemann integral. So it boils down what you want. One feature you want generally is that if you have a Euclidean setting, you want to get this as a special case, and that's the case here, and it's also the case for the Fréchet mean. So here, data example just for Fréchet means. These are one-dimensional distributions. The sample are these gray densities here. This is expressed in terms of densities of H at des for 32 countries. This data is publicly available, was collected in the Max Planck Institute of Demography in Germany. And so you have here the H at des distributions in 1983, and the red dashed curve is the Fréchet mean, and the same in 2013. So these H at des distributions are available for every year, and you can see the Fréchet mean here very well summarizes the features of these densities. And also you can see that the density, the Fréchet mean moved to the right from 1983 to 2013. That's the extension of longevity that occurred in this 30-year period. But you can see the variation is much higher in 2013 across different countries than it was in 1983, right? So the, particularly the Fréchet mean is not deterred by different modes here. It has a nice single-moded density function. Okay, so that shows you here, this picture shows you why Wasserstein metric for which this is calculated is works very well for statistical applications in one dimension. And this brings me now to the issue of variation. So of course, there is the well-known Fréchet variance, which is also in Fréchet's paper in 1948, which means that instead of looking for mu plus, you have the mu plus now, and you just look at the average distance squared of the data x to mu plus, and that's your Fréchet variance. Very straightforward. And then you can, under entropy conditions, that's where the value of entropy conditions comes in, you can actually then get a central limit theorem for the Fréchet variance. But you need to make the connection to entropy condition to do so. And this central limit theorem proved very useful to develop an object ANOVA. That means you want to test different groups whether they have the same means, for example, the same Fréchet means, and then you can use this, this result here to develop a test. If anybody has a question, just interrupt me, please. Okay, now we want to move a little further to characterize the distributional features of our sample. And if your data is in R1, it is very well known, I mean, this is statistics 101, that if you take the sample variance, you can, which is the square difference of the data to the mean, it can be equally expressed as pairwise differences squared, right? So this is the same in real in R1, and also this is true in any Hilbert space, because by linear operation you show this equality. Now what's interesting, it's not true in a general metric space. Then we lose this equality. It's not there. That means for variance, we have a very simple second version of variance, which just takes this formula. So Fréchet takes this approach here, right? And you got a Fréchet variance from here. But if you want to go from the right-hand formula, you are led to a different kind of variance, which we call metric variance, where you take the difference between two data that are from the same population, but X prime is an independent copy of X. So that's a second measure of variance. And once we are thinking about distances, then you can go further. You can think about what can I learn from distances about my sample of metric object. Okay, so that a key tool which we are developing for this is the depth profile of any point small omega in your metric space capital omega. So you take the point small omega and you take a ball around it with the metric that you have in your space, and you increase the radius of the ball, and you got a CDF, a cumulative distribution function. So this is a distribution here, F omega. And so these F omega are now indexed by the elements of your space. For each element of your space, you have one such distribution. And they will be used to inform about the relative location of this element small omega relative to the population. And that, of course, gives you an idea about the depth. How deep is that omega relative to the others? So we have that our population has a distribution P. And you can then define a stochastic process that's indexed in omega. And it's well defined, can be shown that it's well defined and has this as f omega as its one-dimensional marginals. And now, since these are distributions, we can employ, and one-dimensional distributions, optimal transport is very easy, right? Because there is nothing to compute really. The push-forward map from a distribution f omega to any other fx is just the probability transform given here. And you have optimal transport maps, which are also very simple. They are defined here. And now we want to use two things. We want to use the amount of mass that the optimal transport is transporting on one hand. That's here given by the first integral. So you have here the mass in absolute value integrated over the distribution of the starting f omega, where you start the transport. So this gives you the total mass that's transported. It turns out it's just the L1 metric of the quantile functions. And that's the mass. And secondly, we have a sign, because we may predominantly move mass to the right, or we may predominantly move mass to the left with these operations. So there is a sign associated to this overall mass transfer. And here's an illustration of this. So this is a very simple situation where you have a two-dimensional Gaussian, which has mean 0 and covariance 2, 1. And the transports for a point 2, 2, which has this depth profile here, the black dashed curve. So we transport this to four test points. The center of the distribution 0, 0, and then points that go further out from there 2, 0, 4, 0, 6, 0. And here are the transports. So if I start with this point 2, 2, and I transport to 0, 0, I have to transport to the left. 0, 0 is more central, right? So my transport goes to the left. This is the transport. If I transport to 2, 0, it's a little bit less negative, and there's less transport. And then I go further out, I get 4, 0, and 6, 0, right? So the profile, the depth profile densities for those 5 elements are shown here. So blue, dark blue is the most central one, that's the 0.00. Red is the most distant one, that's a 0.60. And the test point by which I start these transports for illustration is 2, 2, 2, the black dashed. So you can see that these depth profiles tell you actually something about the centrality of the data using this transport. So we use this then to define transport lengths to measure the centrality of any fixed element omega with respect to PP, is the distribution of your population of which you take a sample. So the proposed transport rank is just taking the sign and taking the transported mass and then taking the expectation. So small omega here is fixed. That's the point for which you want the transport rank. And capital X is distributed according to your population, that from which you draw a sample. So the larger this transport rank is, the more central you are. And so you can then, of course, make this empirical. So in the empirical version, you take just one element, let's call it xj, of your sample, and you only want to check the centrality of each sample element. So we take a sample xj, and then empirically, we use the empirical transport ranks to check how deep is xj at one point. Then we can define a transport median, which means the most central points in our metric space. Here we just take the set which has maximal transport ranks. This is a set, we don't know how many points there are. So this is just the argmax of the transport ranks in terms of elements in omega. There is an invariance for this. You can show that these are invariant under bijective isometric maps. And if your space actually allows affine transformations and rotations, like if it's a subset of RP, for example, then you can show that everything stays invariant under such operations. Another feature that one likes with depth is the center outward ranks. So for that one, that's possible to get if you have point omega plus around which your distribution concentrates. And that means the following: if you are further, so omega plus is a putative center of your distribution. If you are going further away from omega plus, that means omega 1 is closer and omega 2 is further away from omega plus, then your depth profile for omega 1 is larger. That means the CDF is larger. That means the point omega 1 is more central. And then we call, if that exists, it may or may not exist, we call omega plus a mode of P. And if a mode exists, it's unique, and the transport median and transport mode coincide, and the transport ranks decrease as the distance from the mode increases. We can also define metric depth quantiles. So you have level sets of points where the rank is the same. You have nested super level sets, it's just what's above those level sets. They are nested, and then you can define depth quantiles by selecting a level zeta, and then you find their rank alpha star that belongs to zeta such that the mass in the super level sets is zeta. So we get something like depth quantiles from this for those metric spaces where we have the entropy conditions. There are a couple of asymptotic results. So you can, first of all, think about this stochastic process I mentioned before, which is indexed in omega, element of your metric space, and in T, which is just a one-dimensional real. And this can, under certain conditions, converges to a limiting Gaussian process, zero mean Gaussian process, of which the variance you can write down, but it's hard to empirically assess it. You can also show the convergence of the transport ranks as a 1/² n rate, and also the convergence of the transport median sets in terms of the Hausdorff metric. So these are sort of asymptotic justifications of these notions. And now let me show you an example. This is again H@S data for 32 countries and for males. And so on the left is a two-dimensional MDS plot using the Wasserstein distance for this H@S depth profiles. Okay, so you have the depth profiles. You take the Wasserstein distance and then you do a Wasserstein, and then you do a two-dimensional representation of this with MDS. And you can then apply a clustering and represent the cluster centers as the corresponding densities, the depth profiles of the cluster centers, which are shown here. So you can see the most central cluster is the dark blue one: Denmark, Luxembourg, Belgium, France, Austria. And then we move outward. Russia is in a cluster by itself. It's the most outlying of all. Here the same again, but now with the transport ranks affixed to those countries. And you can see again, Russia has the lowest rank, and the cluster we had before has the highest rank. So it's, you rank those by outlyingness. And you can do what we call a nested circle plot. So here you have the different ranks. So the red outside circle has the lowest ranks, and the inside circle here has the highest ranks. And if several countries have the same rank, we use the distribution, that's why we use the distance in the object space to space them along the circle. For example, Czechia is here, and Taiwan is here, and Portugal. So Taiwan, Portugal are close, they have the same rank. these two are close. Check here is on the other side. But they have the same rank. So they have the same outlyingness, if you wish. Recently, we also discovered that test profiles can be used for inference. So if you want to test that two populations of object samples are the same, you can use these depth profiles because if you take those of xi with respect to x, the distribution which are distributed according to p1, and y which are distributed according to p2, and vice versa for the y's, then all of these coincide. And the null hypothesis that the distributions are the same. And that motivates a depth profile-based test statistic, which just uses this. And again, we can derive the asymptotic behavior under entropy conditions. And we obtain that you get a limit distribution which relates to independent standard normal random variables and certain eigenvalues of a random matrix, of which you take the expected value. So here an illustration from neuroimaging. So you have brain connectivity networks of 264 by 264 SPD matrices, symmetric positive definite matrices, and you want to compare aging. Okay, so 55 to 70 is the starting point, which are represented in this data, and then you go out to age range 1896. We know from neuroscience that these connectivity networks are different for older people than for younger people. So basically, this is just a check whether the test can pick that up and how fast does it pick up the change. Okay, so this is sort of a pseudo simulation because we use real data, but we sample repeatedly from those data, so we can get a power curve, empirical power curve. And so the test statistic I mentioned is the green one. We have different versions. The red and the yellow are different versions of the same test idea. And the dotted here is the energy test, which is usually very successful. The dashed blue one here is the graph-based test. What you also want is that at 5570, you keep the level of 0.05. Which some tests do, some other tests do not. This shows that this test has promise in some applications. Okay, so this was my first part. I'm moving to the second part, which is regression. Okay, so depth was to explore samples and compare two samples. Now regression. So regression has been well developed in Hilbert space. So when our random objects are functional data, in other words, then we have many models available, and they have been very well investigated over many years. The first such model is the functional linear model, which is implicit, not explicit, in Greenlander 1950 already. So if you take xy to be jointly Gaussian, you find that ey given x, C-mean-centered, it's just a linear model here with a so-called parameter function beta st. In the meantime, many other models have been investigated, concurrent, several versions of additive models, etc. So this is very, very well developed, this field of functional regression, to the point that there are not actually that many new models coming up these days. Okay, the situation is very different if we are in a nonlinear spatiometric space. In this case, there are no linear operations, and therefore, basically, all the previous models don't work. You have to do something else. There have been some modeling approaches, for example, Lecture 2013 for this case. One thing is that the question becomes tricky how you model noise. Okay, in usual regression, if y is a scalar, we add noise, right? Plus epsilon I, that's your noise variable, which is independent of the predictor, mean zero, etc. How do we do this in metric space? It's not clear at all. You have to think about it. That just shows you a little facet how things are very different in metric space compared to Euclidean space. So we have the following model here that we say, okay, you perturb your object X in some ways. You perturb it, you get X tilde. And then X should be coming back if you take the object that minimizes all the squared distances to the perturbed object. Again, if you have this definition, P of X as your perturbation or error, you get back to the usual thing in the Euclidean case. One sanity check usually is you want to get back what is well known to work in the Euclidean case, in case your space is a Euclidean space. And that's the case with this approach. A general sort of framework, if X is in RP, p-dimensional, and Y is the object, is that in this case, there is a way to extend Fréchet means, which of course is the main location measure for metric space value data, to conditional Fréchet means. So what we really look at is we want to be able to condition on a predictor, the Fréchet mean. So we look for conditional Fréchet mean, and it turns out that if you use a weighted scheme for the minimization that constitutes a Fréchet mean, you can work this out and you get convergence for such an implementation of the conditional Fréchet mean, where the weights that appear here are derived from Euclidean multiple linear or local regression. And you can use any metric that satisfies, where the space satisfies the requisite entropy conditions. One thing that's very important is that these weights are negative. They are not constructed, cannot be constrained to be positive. You do not get consistency if the weights are positive. So the weights are partially negative. That makes additional difficulty here. And they have to be. So it's not a simple issue of a weighted Bayesian or something like that. It's much more complex than that. You can also show, for example, properties. Of course, Peterson has already the basic properties, but you can also get uniform convergence. We found recently a way to prove it for non-parametric weights. So these weights come from either linear regression or any local regression. Let's say kernel method, kernel smoothing, local linear polynomial smoothing, or multiple regression. They all are weighted averages of the Y's, of the responses. As long as you can write your preferred regression model as a weighted average, you are in business with this and you can derive this. So if you have a uniform convergence result, it can be used for time warping, for example, of object valued processes where the time has a random variation. And that does happen. There are relevant examples for this. A second extension of interest is to trend filtering with Lin. So here we have sequences of random objects, and we want to not smooth them, but we want to fit a step function to them. And why is this possible? We can do a total variation penalty because in object space, you can define total variation. Once you have a distance, a total variation can be defined. P is a partition, you make this finer and finer, you go to the limit, and that's your total variation in object space, which exists. That's the key to this. And so the theory is involved. It requires a lot of geometric concepts, but you can show eventually consistency of this approach, which is an extension of the one where you have just scalars. And is a sort of machine learning like this as trend filtering. So if you use this for, let's say, the data from Russia, which are kind of check it, right? So this is Russian males mortality. Again, I apply this to distributional data, HRS distributions. For Russia, males 1959 to 2012 or 13. Here is the raw data. These are heat plots. You look on top of the density, right? So that if the density is very high, it's red or black. So you look on the density from the top, And you see it's quite ragged, right? There are tons of variation here. Now, if you run the trend filtering through this, the object trend filtering or Fréchet regression with total variation penalty, as we call it, then you fit a step function, right? And that step function is useful to detect change points in such data. For example, here, you can very clearly see there's a huge jump in 1992. There's a huge jump downwards. So the male mortality got very bad in Russia suddenly. And then it stayed very bad for a long time until about 2005. And then it's in many small steps. So these are small steps. The function, this fit can have many small steps and it can have big steps. It improves. So this is a step function fitted to distributional data with this Fréchet regression method and total variation penalty. Okay. Now, generally, a second approach is that we are in a metric space, but we don't have metric space regression methods except maybe this Fréchet regression. So the classical way is that you look for linearity one way or other. So you want to aim at a regression model that is possible to transfer in a linear space. So you want a map of your metric space to linear space in which you do the regression, then you map back after. The classical way to do this is Schoenberg, 1938. Jointly with Auenschein 1950, because what they show is that if you have a space such that D square is a kernel of negative type, which almost all metrics are that we consider, you can construct a reproducing Hilbert space such that there is a one-to-one map from your metric object space to a subspace of the Hilbert space. That's a bit of a problem because subspace is not good enough. If we do a regression, we normally cannot be constrained in a subspace. The regression can go anywhere. So the reverse map is a problem here because we only map in subspace. For other spaces, you can construct explicit maps that map to linearity. For example, for one-dimensional distribution, there is a so-called LQD transformation, which is a one-to-one into a Hilbert space. So then you are in L2, you map your distributions into L2 space. There you do whatever regression you want, like I showed before. The Hilbert space regression, very well developed, tons of models to choose from. Do your favorite model there, transform back. Or you do the tangent bundle. That's sort of the classical method because that's also proposed already by Fletcher 2013. So if your data is in some sort of Riemannian manifold, at least you have Riemannian operations. Doesn't have to be a Riemannian manifold because Wasserstein space is not, but it has Riemannian operations. Once you have Riemannian operations, then you can put tangent planes on your space and you map forward with the log map and then map back hopefully with the exponential map in the Riemannian sense. So you map forward into your tangent space, do your regression there, and then you map back. We have developed this as a so-called Wasserstein regression for one-dimensional distributions. And it also works, of course, for spheres. For example, if you have the Fisher-Rao metric for distribution, you can use the Hilbert sphere or any other sphere as P. There's, however, a problem. Because only on a cone, on a convex cone, you can actually usually define the reverse map. It's not defined on the whole tangent space that uniquely. And that's a big problem in application. So again, we are hamstrung by the fact that we only map in a subspace of the linear space in a one-to-one sense. Similar to the Schoenberg map, has the same problem. So, but it happens that in very few applications, you hit this reverse problem. So if you apply it to data, usually you are okay. So here is the Wasserstein regression for HLS distributions. And we can see that it works quite well. So we have predictors, the one-dimensional HLS 1983 responses in 2013. And For Italy, we have a very good prediction. Japan is observed is blue and predicted is dashed by, we use a functional linear model in the tangent space. A little worse here for, sorry, Japan is better than expected. Ukraine is a lot worse than expected. Wasserstein discrepancy is relatively big. For US, it's a more complicated picture. The shape is different from the one which is predicted. How much time do I have? Okay. Another way is that we recently developed is actually the idea that you should not go out of your space, of your metric space. You should stay inside with your regression. So don't map to a linear space. Stay inside and try to do something there. And that one works if you have two things. One is you have to have a geodesic space. I'm running short of time, so I'm not explaining the total details here. The second is ubiquity of transports, which means if I have a geodesic from between 2 points and I have a third point, I need to be able to apply the same geodesic to the third point. That's possible on spheres. It's also possible on the Wasserstein space and other spaces. In this case, we can then define some sort of algebra on the transport space, which means we have inverse transports. We go from A to B and then back from B to A. We can concatenate two transports as like addition. And in some cases, like the Wasserstein's case, Wasserstein space, for example, we can define a scalar multiplication by attenuating a transport. So essentially what you do is you have a geodesic from A to B, and you go only a certain part along this geodesic. If alpha, the factor by which you multiply is between -1 and 1. So you have a geodesic forward, you have one backward because the inverse exists. You go a little bit, or you go a little bit backwards. If your alpha, the factor, is bigger than 1, then you just concatenate transport. So let's say it's 2.5. I take one transport, another transport, the same one, and then 0.5 of the same one. So that's here for the Wasserstein transport exemplified. So the identity is dashed in terms of quantile functions for the transport. Let's say you have a transport here, the black one, and you can make this to 1/2 or -1/2, whatever you want. And this can be applied for autoregressive modeling. That's what we did here. So you have an autoregressive model for distributional data or for geodesic spaces where you have this ubiquity condition. This has to be satisfied. Well, I don't want to explain this maybe right now. This is just a graphical illustration of the model in time series context, autoregressive one. Brought some consistency, but I'm running out of time, so let me come to my last slide. So the theoretical underpinnings of this potentially emerging field of metric statistics are metrics, geometry, empirical processes, and connections to Hilbert spaces. Maybe there are other important concepts. We have seen that transports in geodesic spaces, optimal transports in Wasserstein space, especially in the one-dimensional Wasserstein space, are key concepts. The choice of the best metric is an open problem. You want a nice geometry if you can, like geodesic should exist, or at least maybe you can get a Hadamard space, depending what you have. Inference is not very well developed, I would say. There are some inference methods, but it's not well developed. So I would say it's in its infancy. There's a lot of work to be done. The interpretation of metric models can be difficult, but I would say it's very essential if you are statisticians and we work with some people in applied fields like neuroimaging. They don't like necessarily a black box. What we can provide, contrast to machine learning, is that we have interpretable models. So we want them to be interpretable, very important. Finally, the theory methods for metric space-valued stochastic processes and also longitudinal data are of particular interest and are challenged. There are some preliminary works, I would say, but certainly this deserves much more attention.